Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at the Gram-Schmidt algorithm. So in this topic we will learn about the idea of the best approximation of a given vector by a collection of m mutually orthogonal vectors. Based on this information, we will define the Gram-Schmidt algorithm for taking a set of m arbitrary vectors and returning a collection of at most m mutually orthogonal unit vectors. We will also look at examples as we go through these steps. Now, suppose that we have two vectors, u1 and u2, that are orthogonal. That means that neither contains any information about the other. In other words, the best approximation of u1 as a scalar multiple of u2 is 0 times u2. That is the zero vector. Similarly, the best approximation of u2 as a scalar multiple of u1 is 0 times u1, which is again the zero vector. Recall, however, that the best approximation of a given vector v of either of these two is found by simply calculating the projection onto those two vectors. So the best approximation of v as a scalar multiple of u1 is the projection of v onto u1, and the best approximation of v as a scalar multiple of u2 is found by calculating the projection of v onto u2. Now, question. What is the best approximation of v as a linear combination of those two orthogonal vectors u1 and u2? Well, as before, what we want to do is minimize the distance between v minus alpha 1 times u1 minus v alpha 2 times u2. This is the equivalent of minimizing the square of that norm, which is the inner product of that linear combination of vectors and itself. We can now, in the same way as we did before, apply the rules of the inner product to get that this is equal to this longer expression. In this longer expression, however, you'll notice that there are two cross terms. There's the inner product of u1 and u2 and the inner product of u2 and u1. But we said that these two are orthogonal, and so consequently we can cancel those out. Also, assuming that these are real vectors, then the inner product is symmetric, so we can now simplify this function we'd like to minimize to this expression here. Now, notice that if we differentiate with respect to alpha 1, alpha 2 disappears. And if we differentiate with respect to alpha 2, alpha 1 disappears. So we can actually minimize each of these independently. We can find alpha 1 and alpha 2 independently, and if you'll note, the alpha 1 and alpha 2 that we find are the projections of v onto u1 and the projections of v onto u2. Consequently, if u1 and u2 are orthogonal vectors, then the best approximation of any vector v as a linear combination of scalar multiples of u1 and u2 is to simply calculate the projections of v onto each of them and add them. Okay, that makes sense. Beyond the scope of this course, but you can work it out yourself, proof by induction actually, given m vectors, all of which are mutually orthogonal, then the best approximation of v as a linear combination of these vectors is just the sum of the projections of v onto each of these m vectors. Okay, so this requires us to have orthogonal vectors. Next, consider the work that is required to calculate this best approximation. In every single case here, we take the inner product of u1, u2, all the way up to um with the vector v. Not a problem. If v changes, we have to recalculate all of them. But take a look at the denominators. If we already have u1 through um, would it not make more sense to normalize each of those vectors u1 through um so that the denominator becomes 1? Consequently, we would reduce the work that's required by half if we simply normalized the vectors u1 through um. Now the best approximation of v as a linear combination of these mutually orthogonal and normalized vectors is found by calculating this linear combination. Nice. Now, suppose that we have m vectors, u1 through um, none of which are necessarily normalized, and no two of which are necessarily orthogonal. Can we convert these m vectors into an associated collection of at most m vectors, all of which are unit vectors and all of which are mutually orthogonal? All right, for this, we do have such an algorithm, and it is called the Gram-Schmidt algorithm. Okay, let's go through the Gram-Schmidt algorithm. Step 1, normalize the first vector. That is, define u sub 1 cap to be u sub 1 over its 2 norm. So therefore we have normalized u1. Step 2. Subtract from u the projection of u onto u1 cap. Now, the arrow here means replace. So I want to replace u2 with the original value of u2 minus the projection of u2 onto u1 cap, because we have by now calculated u1 cap. Now, if u2 after this is 0, that means that u2 was actually a scalar multiple of u1, so it contains no additional information. Discard it and just continue working with u1 cap. Otherwise, normalize the second vector. So we define u2 cap to be this new u2 vector we calculated over its 2 norm. All right. Now, suppose we have two vectors u1 and u2. We can see that these two vectors are not normalized, as they both have entries greater than 1. Also, we see that they are not orthogonal, for the inner product is 5.25 minus 9, which is not equal to 0. So let us apply the Gram-Schmidt algorithm to create two vectors u1 cap and u2 cap, both of which are normalized and they are orthogonal to each other, and they contain all the information of these two vectors. Step 1, normalize the first vector and assign that to u1 cap. Well, the 2 norm of u1 is 2.5, and dividing both entries by 2.5 gives us the vector 0.6, negative 0.8. Okay, next. Replace u2 with u2 minus its projection onto u1 cap. All right, so here we see u2 minus the inner product of u2 and u1 cap multiplied by u1 cap. Well, that's equal to 3.5, 4.5 minus negative 1.5 times the vector 0.6, negative 0.8. And if you work that out, you get the vector 4.4, 3.3. Now, you will see that that vector is not normalized, but it is actually orthogonal to the vector u1 cap. So the next step is to simply normalize that vector. So u2 cap is now defined to be this new u2, which is 4.4, 3.3, divided by its 2 norm, which, if you were to calculate it out, is 5.5. So dividing each of the entries by 5.5 gives us the vector 0.8, 0.6. All right, so we note that these two vectors are both unit vectors and they are orthogonal to each other. Note that it would not be difficult to reconstruct the original two vectors as a linear combination of these two new unit vectors, so no information was lost. As we were only dealing with linear combinations of u1 and u2 in the first place, no information was introduced either. Also, given any vector in R2, say for example the vector -7, -20, then we can find that the best approximation of -7, -20 is found by projecting this vector v onto u1 cap and adding to that the projection of v onto u2 cap, which gives us this expression, linear combination here, 11.8 times the first one minus 17.6 times the second one, and that gives us -7, -20. So in this case, the best approximation is actually equal to v. Now, this may not always be the case, so let's look at an example where it is not the case. Suppose we have these two vectors in R4, one -1, one -1, and the second vector 6, -2, -1, -3. Again, neither of these vectors is normalized, and they are clearly not orthogonal, as their inner product is 6 plus 2 minus 1 plus 3, which is definitely not 0. So let us apply the Gram-Schmidt algorithm to try to convert these two vectors into a pair of normalized and orthogonal vectors. Step 1. Assign to u1 cap the vector u1 divided by its 2 norm. Now the 2 norm of u1 here is 2, so we just divide each entry of u1 by 2, and that leaves us this vector here. Step 2. Replace u2 with u2 minus its projection onto the vector u1 cap. All right, so this is just the vector u2 minus, well, we could calculate it out. It would be 0.5 times 6 plus -0.5 times -2 plus 0.5 times -1 plus -0.5 times -3. If you add those up, we get +5. So we subtract 5 times the unit vector u1 off of the vector u2. This gives us this vector here. And if you look closely, you will observe that this vector is not normalized, but it is now orthogonal to the vector u1 cap. Nice. So now let's just normalize it. So to normalize this vector, we just divide the new vector u2 by its 2 norm. And if you were to calculate the 2 norm of that vector, you would find that it is equal to exactly 5. Dividing each entry of the new vector u2 by 5 gives us the vector 0.7, 0.1, negative 0.7, negative 0.1. And you can see that that is going to be orthogonal to the vector u1 cap. Thus, we have the following two normalized and orthogonal vectors in R4. The best approximation of this vector in R4 can be found by projecting this vector onto u1 cap and adding to that the projection of this vector onto u2 cap. So here's that calculation, and the inner products are 6.5 and negative 11.3 respectively. And if we calculate these, we get this vector here, which isn't that far off. And in fact, this is, of course, the best linear combination of these two unit vectors that approximates the vector v. Any other linear combination of u1 and u2 cap must be further away from the vector v. Now, returning to the Gram-Schmidt process, suppose we had a third vector in this collection, u3. Well, in that case, subtract from u3 the projection of u3 onto u1. That is, u3 is now assigned to the original value of u3 minus the projection of it onto u1 cap. Now, if u3 is 0, then it was simply a scalar multiple of u1, so it contains no new information about u1. So discard it. Otherwise, subtract from this new u3 the projection of u3 onto u2 cap. So we've removed any information in u3 that's already in vector u1. We are now going to remove from what's left of u3 any information that is also in the vector u2. So u3 is once again replaced by the new value of u3 minus its projection onto u2. Okay, now if at this point, once again, u3 is the 0 vector, then it was actually a linear combination of u1 and u2, and therefore it contains no new information. Discard it. However, usually it will not be the 0 vector, and so we now have a third vector that is orthogonal to both u1 cap and u2 cap, and so all we have to do now is normalize it. So we define u3 cap to be this new vector u3 all divided by the 2 norm of this vector u3. Now, suppose we have these 3 vectors in R4. Now, we have already applied Gram-Schmidt to the first 2 vectors, so we found the 2 unit vectors u sub 1 cap and u sub 2 cap. Thus, to create a collection of 3 unit and mutually orthogonal vectors, all we have to do now is apply Gram-Schmidt to u3. Thus, to make u3 both orthogonal to the first 2 vectors and normalized, we just perform the following steps. U3 is first assigned U3 minus the projection of U3 onto U1 cap. So in this case, we have the vector U3. We calculate the inner product of U3 and U1 cap, which is -7. And so therefore we add 7 times the vector 0.5, -0.5, 0.5, -0.5. That gives us the vector 5.5, -0.5, -8.5, -2.5. Next, taking this new U3 vector, we now replace it with this new vector minus this vector projected onto the vector U2 cap. And so here we see that operation. So the inner product of this vector U3 and U2 cap is 10. And therefore we subtract off 10 times the vector U2 cap. This gives us the vector -1.5, -1.5, -1.5, -1.5. Well, now all we do is divide U3, this new U3, by the 2 norm of this new U3, which happens to be 3, and assign that to U3 cap. And this turns out to be the vector -0.5, -0.5, -0.5, -0.5. Thus, we now have these 3 unit vectors that are all mutually orthogonal. If I take the inner product of any 2 of these, the result will be 0. Thus, the best approximation of this particular vector v in R3 is found by simply adding the projection of this vector onto each of these 3 unit vectors. Here's that calculation, and the result is this vector. Once again, we see that this is even closer to the vector v than our previous approximation. After all, we have one more vector we are adding to this expression. Now, suppose we have already applied the Gram-Schmidt algorithm k-1 times, and we now have a kth vector that we would like to add into this collection of normalized and mutually orthogonal vectors. Well, what we're going to do is we are simply going to subtract from UK the projection of UK onto U sub L cap, where L goes from 1 to k-1, at least whenever we did not discard that vector. So first we replace U sub k with U sub k minus the projection of U sub k onto U cap, U sub 1 cap. Then we do the same, but now we subtract off the projection of whatever's left of U sub k onto U2 cap. We keep on doing this k-1 times, and with the last step we subtract from U sub k the projection of that vector onto the vector U sub k-1 cap. Okay, if at any point U sub k ended up being equal to 0, we discard this vector. However, assuming that it remains, we now just normalize this vector and assign it to U sub k cap. So, to summarize the algorithm itself, given m vectors u1 through um, To convert these into a collection of mutually orthogonal unit vectors, start with u1, normalize it, and assign it to u1 cap. Then, letting k run from 2 to m, do the following. First, subtract from u sub k the projection of it onto u sub 1 cap. Repeat this over and over again, each time subtracting from u sub k the projection of u sub k onto each u sub l cap that was not discarded, where L goes from 2 to k minus 1. At the end of this process, if u sub k is equal to the 0 vector, then discard this vector. Otherwise, normalize u sub k and assign it to u sub k cap. Now, it's always important to remember, in this algorithm, we are changing the value of u sub k each time we subtract from it the projection of that u sub k onto any other unit vector. Now, one warning. Before you look online, there are two forms of the Gram-Schmidt algorithm. The most common one that is taught at the undergraduate level is not numerically stable. What that means is it works great for toy examples that are taught and given at the undergraduate level, but the algorithm will fail when the vectors are actual numeric values. The algorithm that was taught in this class, which you have just seen, is more numerically stable. That means it will give a better answer, and you will cover the concept of numerical stability in your second-year course on numerical analysis and methods. So, following this topic, you now know that you can easily calculate the best approximation of a given vector v as a linear combination of mutually orthogonal vectors by simply projecting v onto each of these vectors and adding the results. You also understand that the Gram-Schmidt algorithm can take a collection of arbitrary vectors, that is, vectors that may not be orthogonal and may not be normalized, and convert them into a collection of mutually orthogonal unit vectors that contain the same information that the original vectors had. That is, we can always recreate the original vectors with linear combinations of these new mutually orthogonal unit vectors. Here's the references, acknowledgements, the colophon, and a disclaimer. Cheers!